Okay, so welcome back. We have begun to realize, think more deeply about, because you guys already knew that these relationships between volume, temperature, and pressure of gases, we already knew that they existed. We didn't really think about them daily, sort of thing, but now we're kind of solidifying that understanding with what we call the ideal gas law. So let's have another opportunity to kind of use, maybe not the ideal gas, we'll decide which gas law we have to use to answer this question.
It looks like we're going to need the ideal gas law.
Well, how do you know that?
Because they give us a volume, pressure, and a temperature.
That's right. That's right. So, what does the ideal gas law look like?
I have it in my notes here. Let me see.
Well, you don't need to necessarily have it in your notes. I mean, it is, and you're always going to have, you can always just look it up. It doesn't take a few seconds. But if you sit still and kind of think about those relationships, whether they're directly proportional or inversely proportional, then you can regurgitate the ideal gas law for yourself, right? So let's think about that. Let's choose temperature and pressure. Temperature and pressure. If temperature goes up, and now when we only examine two parameters, we have to remind ourselves that the other parameter, volume, will be fixed, right? Or any other parameters for that matter. So if temperature goes up, how is that going to change the pressure if volume is fixed?
Increasing the temperature would make the pressure go up.
That's right. So what that shows us is that temperature is directly proportional to pressure, right?
Okay.
And then let's see, what about temperature and volume?
Increasing temperature also increases volume.
Very good. So temperature and volume are directly proportional. What is the one that's inversely proportional?
Let's see, that was pressure and volume then.
That's right. Pressure, as the pressure goes up, the temperature goes, the volume goes down, right? And so we say that there is an inversely proportional relationship there, all right? So now let's think about this pressure and volume scenario. Pressure goes up, the volume goes down, right? And that's the example of taking our balloon, has a volume, putting underwater, the pressure is increasing and the volume goes down, okay? So, and we said that for those scenarios, pressure and volume have to be related to each other like this. And let's put in some numbers to make sense of this. If I had 10 liters at 1 atmosphere, and I doubled the pressure, put it underwater, 2 atmospheres, I see that the volume must be now cut in half. If I double the pressure, the volume has to be cut in half. So these inversely proportional ones are related to each other like so. And temperature, which is directly proportional to pressure, for example, has to be related to initial pressure, initial temperature, second pressure, final temperature, right? Has to be related like that. Let's put in some volumes here, or some values here. Pressure, 1 atmosphere, for example. Temperature, 100 Kelvin, all right? If I double the temperature to 200 Kelvin, we would expect the pressure to increase, and we'd see that, yes, the pressure would have to double as well. All right? So when they're directly proportional, this is the way that the relationship has to work. When it's inversely proportional, it has to work like that. So we went through the process and we basically regurgitated that there is this relationship like so, where initial volumes compared to final volumes. So we can plug these in now, right?
Yeah.
So what is our initial volume?
500 milliliters.
So 500 milliliters for our initial volume. Initial pressure?
722 torr.
722. Initial temperature?
Negative 25, but you just got to add 273.
That's right, negative 25 plus the 273. I'll get my calculator so we don't have to use our brain cells any more than necessary. negative 25 plus 273. 248. All right. What's our second pressure?
491 millimeters of mercury. Didn't you say millimeters of mercury was the same as torr?
Yeah, that's right. So I can put in there for the new pressure 491, and that'll be just fine. Okay. Let me sneak this up here just a little bit, give ourselves a little more space. Okay, there's our new pressure. What's our new temperature?
Oh, that's what we're after.
Oh, yeah. So what's the new volume?
2.53 liters.
And the old volume was what?
It was 500 milliliters. So I think you got to convert those to the same units, right?
Yeah. So instead of expressing this in liters, I'll express it in milliliters, 2,530 milliliters. Is that all right?
Yeah, okay.
And then we can solve for our temperature, right?
Okay.
So if you put that into the calculator, you should be able to get out 853 Kelvin.
All right. Sounds good.
Okay, good job. Now, here's another one. A sample of helium occupies 500 milliliters at 1.21 atmospheres. Calculate the volume if the gas of the pressure is reduced to 491 torr. And here's a little helpful conversion factor. 760 torr is 1 atmosphere. Okay, now, why don't you try this one for yourself? Does that sound okay?
Yeah, I can try that one.
Let's give the folks at home a chance to do that. Push pause, try this one for yourself, and see if you get the answer. All right, hopefully you gave it a good try. What'd you get, Fred?
Well, I think that we don't need the combined gas law. Is that right?
That's right, because they only gave us what?
Well, they only give us volume and pressure. They didn't give us temperature.
That's right. Now, it doesn't hurt if you include temperature, or if you use all 3 parameters and you only needed a couple of them, right? That's okay. That's not a big deal. But if one of them doesn't change, then it's not going to influence the outcome, so you really don't need to include it. But we can, again, look at pressure and volume and temperature, and realize here that temperature is not included, and then just leave that out, and then just use PV like that, and we could solve our problem with that, right? So we got 500 milliliters, 1.21 atmospheres, the 491 torr. What is that in atmospheres? 491, how many atmospheres is that? Right? So this is torr, 760 torr for 1 atmosphere. So 491 divided by 760. 0.646 is our new pressure, and then our new volume here will be, you guys can solve that in your calculator, right?
Yeah.
936 milliliters, or 0.936, 936 milliliters, 936 milliliters. Okay, does that make sense?
Yeah, that makes sense.
Okay, very good. One more for you. Why don't you guys work on this one? Push pause, work on it. Goes from 25 degrees Celsius to 200 degrees Celsius, and we want to know what the resulting volume is. Okay, did you work on it?
Yep, I did.
So how did you do it?
Well, it's just temperature and volume, and those are inversely proportional, so you said that it has to go temperature over volume.
Right, or volume over temperature. Either one of those will work. 1, 2, 2, right? So the initial volume, 22.4, 25 degrees Celsius, that's 298 Kelvin, right? 200 degrees Celsius, 473 Kelvin, and then we're solving for our temperature there, or our volume. So we got 22.4 times 473 divided by 298. So 35.6 should be our volume, 35.6 liters. Okay, good. There's one more relationship that we're going to include in the mix, and we've already introduced this to you, but not officially. This is called Avogadro's principle. Same Avogadro that related the, or identified 6.02 times 10 to the 23rd units per mole of material, right? Per mole of whatever it is. And the relationship here is that there's a direct relationship between the volume and the moles of gas that are in that sample. And, you know, ta-da! That's amazing, right? If you put in one breath of air into your balloon, the balloon has a volume of X. If you put 2 breaths in, it should have a volume of 2X, right? And that's all that it's saying. So again, nothing terribly surprising here. All right. Again, I mean, it has it written up here, so I don't have to write it down there, but a directly proportional relationship between volume and the moles of gas in the balloon, which, if you want to look at initial and final scenarios, can be related thus. Now, why does this principle become significant to us? Is because of our chemical reactions, right? Here's a chemical reaction. This chemical reaction says, well, can you translate it for me, Fred?
Yeah, okay, I can translate it. You mean like, what do you mean translate?
Well, you know, so this is 1 mole of nitrogen.
Oh, yeah, like that, okay. 1 mole of nitrogen gas plus 3 moles of hydrogen gas yields 2 moles of ammonia gas.
Very good. And that's how we've been taught to translate it. But now that we just saw that there's this relationship, directly proportional relationship between volume and moles, we can also say 1 liter of nitrogen gas plus 3 liters of hydrogen gas yields 2 liters of ammonia. So the stoichiometry that would generally relate to the moles of material can be expressed in terms of liters of material. And now that's only if we're talking about gaseous material. If this is solid and liquid, then it's not true that there's a direct relationship between the volume of the material and the moles of material, because different materials have different densities and different. So if this was ammonia that was a liquid, it would have a different, if 2 moles of ammonia liquid would have 2 different volume than 2 moles of liquid water, for example. But because they're gaseous and that there's this relationship between the volume of a gas and the moles that are in the gas, we can now use the stoichiometry to express relationships not just between moles, but liters of material, or any volume for that matter, milliliters. So calculate the volume of ammonia formed by the reaction of 25 liters of hydrogen in excess nitrogen. Well, if I had 25 liters of hydrogen, I can see that for every 3 liters of hydrogen, I'm going to produce 2 liters of ammonia. So, we can use our dimensional analysis and say, I want to know how many liters of ammonia, right? Starting off with 25 liters of hydrogen gas, and I can relate liters of hydrogen gas to liters of ammonia through the stoichiometry. 2 to 3. 2 liters of ammonia are created for every 3 liters of hydrogen gas that go in. So 25 times 2, 50, divided by 3, and that'll be our liters of ammonia. Okay? Did you see how we can now express our reactions that are completely gaseous in terms of liters, just the way we could express them in terms of moles?
Okay, I got it, yeah.
All right, now here's a different one. Let's see if you guys can work on this at home and get the answer. Push pause, and then after you got the answer, push pause or push play and come on back and we'll see what you did, okay? Okay, how are we going to do this one, Fred?
Pretty much the same thing, right?
Yeah, but what's different?
Well, it's a limiting reaction problem.
That's right. It's a limiting reaction problem, isn't it? How could you tell?
Because they told us about the volume or the amount of 2 reagents.
That's right. So we have to, again, do our dimensional analysis. How many liters of ammonia? 125 liters of hydrogen. For every liter of hydrogen, for every 3 liters of hydrogen, 2 liters of ammonia. But then I have to repeat that for, NH3. I have to repeat it down here for 50 liters of nitrogen for every 1 liter of nitrogen.
Where'd you get that one?
The stoichiometry here.
Oh, yeah. 1 liter of nitrogen for 2 liters of ammonia.
That's right, 2 liters of ammonia. So 50 times 2, that's going to be 100. 125 times 2 divided by 3, what's that going to be? 125 times 2 divided by 3. That's only 83. So, which one's going to be our limiting reagent?
It looks like the hydrogen is going to be the limiting reagent.
That's right. Nitrogen's here. It will allow us to get 100 liters of ammonia, but the hydrogen only allows us to get 83.3 liters of ammonia. So the answer will be 83.3 because hydrogen is the limiting reagent. Okay, good. Good place to stop. We'll see you next time.
Okay.